Hello everyone, my name is Eunchae and I present the paper IMMFAN. It is a hierarchical multimodal fusion attention network for emotion recognition. The table of contents is as follows. Introduction, related works, methods for emotion recognition, experiment results, and conclusions. Introduction. To understand human emotions, data can be collected from humans, such as voice, text, biosignals, and facial expressions. In emotion recognition, a multimodal approach is based on the assumption that the information from each modality is complementary. It is necessary to effectively integrate and fuse information from multiple modalities. This paper makes the following contributions. First, we propose a hierarchical multimodal fusion attention network, called HIMMFAN. It is reducing the model's complexity and improving accuracy compared to the MMFAN. We use cross-attention for solving the problem of the data imbalance. The model to learn patterns of minority classes without relying on a majority of classes. Here is related works. It is image recognition on KEMDY20 dataset. We compare the models using KEMDY20 dataset. MMM utilized the MF mixer structure and combines speech and text data for learning, demonstrating the efficiency of learning with fewer parameters. For data augmentation, MMM utilized an external dataset to evenly distribute the distribution of the remaining emotion waves, except for neutral or conductive. Multimodal decision fusion-based emotion classification model derives predictions from three independent emotion classification models based on voice, text, and biosignals. And the model determines the final value by ensembling the predictions. MFAN views pictures extracted from each modality and classified emotions by focusing on the attention mechanism. Additionally, to address the data imbalance issue, borderline mode was used to minimize noise and augment minority classes. We compared the multimodal fusion model for image recognition. The effectiveness of a multimodal approach can vary depending on the fusion strategy employed, leading to increased or decreased performance. MTF-net, here is two levels of a feature extraction, utterance level and dialogue level. It used a multi-head attention-based fusion mechanism to combine emotion-rich features from visual, audio, and text modalities. Multi introduced to address issues in an end-to-end manner without explicitly aligning the data. Its core features was the directional pairwise cross-modal attention, which attended to interactions between multimodal sequences across distinct time steps. HFCNN used feature-level fusion to combine global features with manually extracted statistical features. It employed a layered incremental architecture within the CNN, setting different conversion kernel size and numbers to extract hierarchical local features from multimodal input signals. For the fusion module, we use cross-attention defined in equation. The similarity between each vector in query and all vectors in key is determined using the dot product known as the attention score. To normalize this score, the submax expansion is applied, where the k represents the dimension of the k vector. These normalized attention scores are then used to compute the weighted sum of the value vectors. Gross attention is a method that uses the output of one modality as the input of another modality, running interactions between different information sources. In this paper, we propose a hierarchical multimodal fusion attention network for image recognition, as shown in the figure. YRSTM model handles temporal characteristics and learns contextual information. On the other hand, the MRP mixer model focuses on learning global patterns and spatial information. The text model uses Roberta and extracts sentence information by using the embedding at the special token named CLS token position. The physiological signals EDA and temp are trained using bi-LSTM models with extracted time series data characteristics. The audio model performs cross-attention for each output. In addition, the outputs of the EDA and temp models perform cross-attention. Finally, hierarchically combined with the output of the text model. After combining the outputs, multi-head attention is used to reduce information loss and identify correlations between input information. In this paper, we utilized the Korean emotional multimodal dataset in 2020, which is a multimodal dataset consisting of spoken voice, text, EDA, and temp, and interbit interval. There is 7 emotions labels: happy, surprise, angry, neutral, disgust, fear, and sad. In this study, we performed the feature extraction considering the characteristics of each modality to use the data as input values for the multimodal fusion network model. For feature extraction of the audio data, we used the waveback 2.0. And for feature extraction of text data, we utilized the lower tag. And for the biometric signals EDA and temp, we use the TS Fresh. Waveback 2.0 is based on the transformer architecture and extracts the 70 representation of the audio data sequenced through the self-attention mechanism. Lower tab, it is after setting the maximum token length, we encoded the text data through the lower tab tokenizer to extract high-dimensional representations of the text data. TSPress, it is based on various statistical hypothesis tests and can automatically extract significant features from each time series data. It is experiment results. We used weighted F1 score and accuracy as evaluation metrics to accurately evaluate the performance of the model in imbalanced data. Table 1 compares the results of emotion recognition using single modality and emotion recognition using multimodalities. The model using multimodalities showed higher accuracy than the model using single modalities. The proposed model in this paper hierarchically combines the MMFAM model structure and designs a fusion network based on the weights of each output. As a result, it reduced complexity compared to the MMFAN and improved performance by 1.87 and 1.8% in terms of weighted Apple score and accuracy, respectively. Conclusion. We propose a multimodal image recognition model called High MMFAN that uses audio, text, and biometric data. We designed a model structure in which modalities are fused hierarchically. In addition, we used cross-attention to fuse features from each modality in a complementary method. As a result, we were able to solve the problem of data imbalance without using data augmentation techniques. In the future work, we plan to explore methodologies that can learn correlations between data, even with many missing values, and improve model performance with less data. Thank you for your attention.